It's funny how some ideas, once you really grasp them, feel like they've always been with us.
Yeah.
So basic, so fundamental.
Yeah, like built into the way we think.
Exactly. But then you start digging into the history of these ideas.
And you find they have these fascinating origin stories.
And it turns out they weren't always there.
Someone had to actually articulate them, make them precise.
Propositional logic is a perfect example. We've always thought about arguments, debated, tried to figure out if conclusions follow from premises.
But the idea of creating a formal system for that, focused specifically on how the meanings of sentences and those logical operators, the connectives, work together.
Right, the ands, the ors, the not.
That really took shape in the 19th century.
Which is kind of surprising when you think about it. I mean, Aristotle was already talking about logic way back when.
He was, but it was more about making observations about how reasoning worked in practice.
The focused study of these very specific logical operators that came much later.
It was a shift from general observations to a really precise analysis of the mechanisms of logic.
And what's really fascinating to me is that this wasn't about discovering new facts about the world, but about understanding how we connect those facts.
It's meta, in a way. Philosophers turn their attention to the tools of thought themselves.
Like they said, let's build a toolkit for dissecting arguments, a precise way of understanding how we move from one idea to the next.
And that's the heart of propositional logic, breaking down reasoning into its most basic components.
Okay, so to really see what's special about propositional logic, let's think about a classic syllogism for a second. All men are mortal, and Socrates is a man. Therefore, Socrates is mortal.
A textbook example of logical reasoning.
Right, we just get it intuitively. But here's the thing, you could also argue that the same starting point, all men are mortal and Socrates is a man, leads to another conclusion, all men are mortal.
Ah, interesting. So now we have two seemingly logical conclusions from the same premises.
And they both feel logical, but the kind of logic feels different.
I see what you mean. The jump to Socrates is mortal feels like it relies on more than just the word and. There's something about categories, about membership.
But with all men are mortal, the connection feels much more direct.
Like it hinges specifically on how that and is combining the two parts.
Precisely. Propositional logic is all about zeroing in on that more direct connection.
It's philosophers saying, let's isolate this type of logical glue. Let's ignore, for now, the other stuff involved in the Socrates example.
So it's a deliberate narrowing of focus to get at something very specific about how we reason.
Exactly. It's a choice. A decision to study one aspect of logic in isolation to understand it more deeply.
All right, so before we dive deeper, let's clarify something. Our source mentions sentential connectives and then propositional connectives. I have to admit, those sound kind of similar to me.
They do, and the distinction can be a bit subtle. Think of a sentential connective as any linguistic element that operates at the sentence level, joining or modifying entire sentences.
Okay, so it's very broad. Anything that connects sentences in some way.
Right. But a propositional connective is more specific. It operates on sentences that express propositions.
Propositions. Remind me what those are again.
They're statements that can be evaluated as true or false, claims about the world that can either hold or not hold.
Got it. So a propositional connective takes sentences that make these truth-evaluable claims.
And combines them in a way that results in another sentence that also makes a truth-evaluable claim.
It keeps us within the realm of things that can be true or false.
Exactly. Philosophers are being very precise here about what they're including in their analysis. They're saying, we're interested in how these connectives operate on this specific type of linguistic element.
So if A and B are statements that can be true or false, then A and B is also a statement that can be true or false. Same with not A.
Perfect examples. Those fit the bill for propositional connectives.
But things like, it is necessary that A, or A implies B, feel different.
You're right, they do feel different, and that's because they're not simply combining propositions in a truth-functional way.
It's like they're doing something more, something beyond just looking at whether A and B are true or false.
Exactly. It is necessary that A is making a claim about the proposition A, about its modal status.
It's saying something about how A is true, not just that it's true.
Precisely. And A implies B is talking about a relationship between A and B, a connection that goes beyond their individual truth values. These are usually considered modal operators, not propositional connectives in the strict sense.
So they fall outside the scope of what propositional logic is trying to capture.
Right. They introduce a different kind of complexity that needs a different set of tools to analyze.
And the conditional if A then B Is that a propositional connective?
That's a classic philosophical puzzle. Some argue it is truth functional, others vehemently disagree.
So even something as seemingly simple as if, then, leads to deep philosophical debates about its logical nature.
It does. It highlights how even basic linguistic structures can raise profound questions about the relationship between language, logic, and the world.
And here's what I find particularly interesting. This whole field, propositional logic, developed without everyone agreeing on what a proposition is.
It's a bit remarkable, isn't it? You might think you'd need to define your basic building blocks before you start building a system.
Right, like figuring out what a brick is before you start constructing a house.
But that's not how it happened with propositional logic. The initial focus wasn't on the deep philosophical question of what propositions are.
It was more practical, more focused on how those connectives function.
Exactly. Philosophers were interested in how these connectives work on entire sentences that have truth values, regardless of the deep metaphysical nature of those sentences.
They were saying, let's look at how these connectives operate on the level of language, on the level of statements that we can evaluate as true or false.
Precisely. They sidestepped the debate about the ultimate nature of propositions and focused on the operational level.
So it's like they said, we can figure out the rules of the game without having to perfectly define what the pieces are made of.
Exactly. It was a pragmatic approach that allowed propositional logic to develop independently of other deep philosophical debates.
Okay, so we've talked about the motivation for propositional logic and the objects it studies, these propositional connectives. Now let's get to the how. How do philosophers actually do propositional logic? What's the formal system they developed?
Well, the good news is that the formal language of propositional logic is surprisingly clean and elegant.
That's always nice to hear when talking about philosophical topics. Sometimes things can get a bit, well,
Messy.
let's just say complex. So this formal language, where do we start?
We start with the most basic elements. Atomic propositional variables.
Those sound important. What are they exactly?
Think of them as stand-ins for simple statements, the most basic building blocks of our logical system.
So instead of writing out a whole sentence like the sky is blue, we can just use a symbol to represent it.
Exactly. We often use lowercase p with a numerical subscript, like P1, P2, P3, and so on. Each p represents a distinct atomic proposition.
Makes sense. Keeps things tidy. And then we have the connectives, of course.
Yes, but initially, to be as general as possible, we don't jump straight to our familiar symbols like wedge
Right.
or V. We use a more abstract notation.
Abstract. How so?
We use a C with a superscript and a subscript. The superscript indicates the arity of the connective.
Arity. That sounds vaguely mathematical.
It is. The arity tells you how many propositions the connective operates on. So C11 would be a unary connective, like not.
Because not only needs one proposition to work. Not A makes sense. Not A and B doesn't quite work the same way.
Precisely. And C12 would be binary, like and or or.
Mm.
It needs two propositions as input.
So C12AB would represent either A and B or A or B, depending on which specific binary connective C12 refers to.
Exactly. This general notation allows us to talk about the structure of propositional logic without committing to specific connectives right away. It helps us see the underlying patterns.
It's like having a blueprint that can be used to build different houses depending on the specific materials you choose later.
A very apt analogy. And then, of course, we combine these atomic variables and connectives to form formulas.
Formulas. So these are the complex, logical statements we can build within the system.
Exactly. And there's a very specific rule-based way to construct formulas. It's a recursive definition.
Recursive. That sounds like it might involve some loops or repetitions.
Well, in a way it does. The definition says, first, any single atomic variable, any p on its own, is already a formula. That's our base case.
So P1, P7, P103, those are all formulas right off the bat.
They are. Then, the second part of the definition says that if you have an emery connective, let's say it's represented by C and M, and you apply it to M formulas.
That's on M formulas. So those formulas could themselves be just simple atomic variables,
Or they could be more complex formulas that were built using this same rule. That's where the recursion comes in.
So you can take formulas, combine them with connectives to get bigger formulas, and then take those formulas and combine them again.
Exactly. It's a process of building more and more complex logical structures from simpler ones. We often use functional notation to represent this, so C and M, A, B, C, means that the connective is applied to the formulas A, B, C, and so on.
It reminds me of how we define functions in math. You take an input, apply a function and get an output.
That's a very good comparison. You can think of these connectives as functions that take propositions, represented by the formulas, as input, and give you a new, more complex proposition as output.
It's a way of formally capturing how logical relationships create new claims about the world.
Precisely. It's a key insight into how logical thinking works. Now, it's important to note that while this functional analogy is useful,
There's always a but in philosophy, isn't there?
well, let's just say it's worth being precise with our terminology. The term propositional function has a different meaning in some other areas of philosophy, particularly in the work of Bertrand Russell.
So you have to be careful not to mix up those meanings. Context is everything in philosophy.
It always is, so while the functional analogy is helpful, it's not universally accepted terminology.
Got it. We'll stick with connectives for now. And our source actually shows some examples of these formulas built up from atomic variables and those C connectives.
They do. They start with a simple one, just P4.
So that's just a single atomic proposition represented by the variable P4.
All right. Then they show C12, P7, P3, which is more interesting.
Because now we have a binary connective operating on two atomic propositions, P7 and P3.
Exactly. And then they get even more complex, showing a nested formula. C22, C11, P1, C11, C12, P2, P3.
Wow, that's a mouthful. And it looks a bit intimidating, all those parentheses and nested connectives.
It does, but if you break it down step by step, it's not too bad. It's like those nested Russian dolls. You just have to open them one by one.
And those parentheses are crucial, right? They tell us how the connectives group together, which ones are applied first.
Absolutely. They act like the punctuation of our logical language, ensuring that the structure of the formula is clear.
So we can build these complex formulas using this recursive definition. But in practice, when philosophers actually use propositional logic, they don't usually write out all those C connectives, right?
Right. They use a more familiar and compact notation.
With symbols like wedge for and or and so on.
Exactly. Those symbols are the shorthand we use to actually work with propositional logic.
It's like learning the alphabet first and then moving on to writing full words and sentences.
A good analogy. And for binary connectives, we usually use infix notation, putting the symbol between the propositions.
So instead of writing C12AB, we'd write A wedge B for A and B.
Precisely. Much more readable, and it aligns with how we naturally express these logical relationships in language.
And the source shows how that complex C formula we saw earlier can be rewritten using these more familiar symbols. It becomes neg AV wedge C.
Much clearer, isn't it? And this ability to translate back and forth between the general notation and the specific symbols is important.
Because it allows us to move between the abstract structure of propositional logic and the concrete way we use it to represent arguments.
Exactly. And when we want to talk about general properties of formulas without getting bogged down in specific atomic propositions, we use formula variables like A, B, and C.
So we can say things like, if A is true and B is false, then A and B is false, without specifying what A and B actually stand for.
Precisely. It allows for a more abstract and general analysis of logical relationships.
It's like doing algebra with logic.
In a way, it is. Now, we've talked about the language and the structure, but we haven't yet addressed the crucial question of meaning.
Right. How do these formulas actually connect to truth and falsity? How do we know if a formula is true or false within this system?
This is where the concept of interpretation comes in.
Yeah.
And the most common and foundational interpretation is the classical interpretation.
Classical. So old school, traditional.
In a sense, yes. It's the interpretation that aligns most closely with our intuitive understanding of logic, and it forms the basis for much of modern logic.
And the core concept here is truth functionality, right?
That's the key idea. The classical interpretation assigns meaning to propositional connectives by defining how they operate on truth values.
It's like saying, here's how and works, here's how or works, here's how not works, but in a very precise, mathematically rigorous way.
Precisely. And in the classical case, we're working with a simple black and white system of truth values.
Just true and false.
Yeah.
No in between, no shades of gray.
Exactly. It's a bivalent system, often represented by for true and for false.
So every proposition, every formula ultimately gets assigned one of those two values. It either holds or it doesn't.
And this bivalence, this two-valued system, is the bedrock of classical truth theory. It's what allows us to build up the entire edifice of classical logic.
Now, the source mentioned something called zero-airy truth functions. What are those? It sounds like they don't even operate on any propositions.
They don't. They're the simplest possible truth functions, representing statements that are always true or always false, regardless of any input.
So it's like saying the sky is blue and the sky is not blue at the same time.
Well, not quite. It's more like saying this statement is always true and this statement is always false.
Yeah.
They're represented by top for always true and bot for always false.
Like axioms in a way. Foundational truths that don't depend on anything else.
In a way, yes. They're the starting points for building up more complex truths.
And then we have unary truth functions, which operate on a single truth value. What's going on there?
Well, with a single truth value, there are only 4 possible things you can do. You can have a function that always outputs, one that always outputs, one that flips, and vice versa, and one that just echoes the input. It's a way of exploring all the possible transformations of a single truth value.
The source mentions something about imposters among these unary truth functions. It seems a bit harsh to call a logical function an imposter.
Well, it's a playful way of pointing out that some of these functions aren't doing anything logically interesting. The ones that always output or aren't really dependent on the input at all, and the one that just echoes the input doesn't change anything either. It's only the truth-flipping function, negation, that truly transforms the input in a logically significant way.
So it's about identifying which functions actually contribute something new to our logical toolkit.
Exactly. Philosophers are always looking for the most essential, most fundamental building blocks. Now, with binary truth functions, things get much more interesting.
Because now we have 2 inputs to play with, so there are more possibilities.
Exactly. And with 2 inputs, each having 2 possible values, there are 4 possible input combinations.
Okay, so true, 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 false, false, true, and false, false.
Precisely. And for each of those combinations, the output of the function can be either true or false. So we have 2 by 2 by 2 by 2 by 2 by 2 equals 16 possible binary truth functions.
Wow, 16, that's a lot more than I expected. The source actually lists them all out in a table, which is quite helpful for visualizing it.
It's a comprehensive way of seeing all the possible ways that 2 truth values can be combined.
And the source, again, talks about imposters among these binary functions. Are there really that many logically uninteresting ways to combine 2 statements?
Well, in a sense, yes. Many of those 16 functions don't really depend on both inputs. Some only look at the first input, some only at the second, and some ignore both and just output true or false consistently. Only a subset of these functions genuinely connect the truth values of both inputs in a unique way.
So we have 16 functions, but only a few of them are doing something truly logically new and interesting.
Exactly. And it's those genuinely connective functions that we associate with our familiar propositional connectives like not, or, and.
So philosophers looked at all these possible ways to combine truth values, and they picked out a few specific ones as the basis for our logical vocabulary.
Exactly. Classically, neg corresponds to the truth-flipping function, the one that turns true into false and false into true.
So neg is true if A is false and false if A is true.
Precisely. And v, or, corresponds to the function that's true if at least one of its inputs is true.
So AVB is true if A is true, if B is true, or if both are true. It's only false if both A and B are false.
Right. And lastly, wedge, or and, corresponds to the function that's true only if both of its inputs are true.
A wedge B is only true if both A and B are true. Otherwise, it's false.
Exactly. Now, these choices might seem arbitrary, but they're based on deep philosophical considerations about how we use these connectives in language and how they connect to our intuitive notions of logical reasoning.
So we have this whole system of formulas built from atomic propositions and connectives, and now we have specific truth functions assigned to those connectives. What does that allow us to do?
It allows us to determine the truth value of any complex formula, no matter how large or complicated, by systematically applying these truth functions.
Starting from the truth values of the individual atomic propositions, we can work our way up, combining them according to the connectives and their corresponding truth functions until we get the truth value of the entire formula.
Precisely. It's a powerful method for analyzing the logical structure of complex statements and determining their truth conditions. It's like having a set of rules that lets you compute the truth or falsity of any argument within the system.
That's remarkable. But it's not just about calculating truth values, is it? There are bigger, more fundamental concepts that emerge from this truth functional framework.
You're right. This is where some of the core ideas of propositional logic come into play. Ideas like validity, satisfiability, consequence, and equivalence.
Okay, let's unpack those one by one. First up, validity. What makes a formula valid in propositional logic?
A formula is considered classically propositionally valid if it's true under every possible truth value assignment. No matter what truth values you give to the atomic propositions, the formula always comes out true.
So these are like logical truth statements that are true by virtue of their form, regardless of their content.
Exactly. They're often called tautologies.
Like A or not A. No matter what A is, that statement is always true.
Precisely. A classic example of a tautology.
And what about satisfiability? How is that different from validity?
Satisfiability is a bit weaker than validity. A formula is classically satisfiable if there is at least one assignment of truth values that makes it true. It doesn't have to be true under all assignments, just under at least one.
So it could be true in some cases, but not in others.
Right. And if a formula is never true, no matter what truth values you assign, it's called unsatisfiable.
Which is basically a logical contradiction, a statement that can never be true.
Precisely. Like A and not A. No matter what A is, that statement will always be false.
So we have valid formulas that are always true, unsatisfiable formulas that are always false, and satisfiable formulas that fall somewhere in between.
That's right. These concepts give us a way to classify the logical status of different formulas. Now, next up is one of the most important concepts in logic, consequence.
Oh, consequence. This feels like the heart of logic, figuring out what follows from what.
It is. In propositional logic, we say that a formula B is a classical consequence of a formula A.
So B follows logically from A.
If there is no truth value assignment where A is true and B is false, in other words, whenever A is true, B must also be true.
So it's about a guaranteed connection between the truth of A and the truth of B. If A holds, B must also hold.
Exactly. It's a fundamental concept for understanding how we build arguments and how we draw valid conclusions.
And what about equivalence? That sounds like it's about two formulas being essentially the same.
That's the gist of it. Two formulas A and B are classically propositionally equivalent if they have the exact same truth value under every possible assignment of truth values to their atomic propositions.
So no matter what truth values you plug in, A and B will always agree on whether they're true or false.
Precisely. They're logically interchangeable within the system.
So if you have a complex formula, and you can prove that it's equivalent to a simpler one, you can essentially replace the complex one with the simpler one without changing the logical meaning.
Exactly. This idea of equivalence is incredibly useful for simplifying logical statements and for proving theorems within propositional logic.
It's like having a dictionary of synonyms for logical formulas.
That's a great way to think about it. Now, the source mentions a connection between propositional logic and Boolean algebra. I remember a bit about that from math class, but how do those two areas connect? They connect beautifully. The language of propositional logic, when restricted to negation, conjunction, and disjunction, or
So just those three basic connectives.
maps perfectly onto Boolean algebra. Think of not as complementation and as intersection and or as union.
Ah, so it's like translating logical operations into set operations.
Exactly. And this means all those familiar Boolean laws like commutativity, associativity, and distribution all have their counterparts in propositional logic. Even things like the law of excluded middle, which says that A or not A is always true.
And double negation, which says that not A is equivalent to just A.
Those fit right in. It shows a deep underlying unity between the structure of logical reasoning and the structure of sets, a connection that philosophers and mathematicians have explored for centuries.
So this mapping to Boolean algebra provides us with a whole set of tools and techniques from math that we can apply to logic.
Precisely. And one of the most useful concepts that emerges from this connection is the idea of normal forms.
Normal forms, what are those?
In propositional logic, a normal form is a standardized way of writing a formula. There are different types, but the most common are disjunctive normal form, DNF, and conjunctive normal form, CNF.
So it's like saying, no matter how complex a logical statement is, we can always rewrite it in a specific standardized format.
Exactly, and the DNF theorem is particularly powerful. It states that any classically interpreted propositional logic formula, no matter how complex, is equivalent to a formula in DNF.
And what does DNF look like?
A formula in DNF is a disjunction, an or of.
So something or something or something.
Of conjunctions, which are ands of.
Something and something.
And some of propositional variables or their negations. So it's essentially a bunch of and statements, all connected by or.
The source gives an example of how to actually construct this DNF for any given formula. They use a hypothetical three-place connective.
Right. You look at the truth table for that connective, and for every row where the output is true, you create an and clause.
So you look at the inputs for that row, and if an input is true, You include the corresponding variable in the clause. If it's false, you include its negation.
Exactly. And then you connect all those and clauses with or. The resulting formula will have the exact same truth table as the original, but now it's in this nice standardized DNF.
So no matter what crazy combination of connectives and variables we start with, we can always find an equivalent formula that's just a bunch of ands connected by ors.
That's the power of the DNF theorem. And there's a similar process for finding the CNF of a formula, which is a conjunction of disjunctions.
So instead of ands connected by ors, it's ors connected by ands.
Exactly. And these normal forms are incredibly useful for analyzing logical statements, for simplifying them, and for proving theorems within propositional logic.
They provide a kind of standardized language for expressing logical relationships.
Precisely. And the fact that we can always find a DNF or CNF for any formula tells us something very important about the expressiveness of propositional logic.
What does it tell us?
It tells us that the set of connectives consisting of just negation, conjunction, and disjunction, V, is truth functionally complete.
Truth functionally complete. This sounds like a mouthful. What does that actually mean?
It means that any other truth function you can possibly define, no matter how many inputs it takes or how complex its behavior,
So any way of combining truth values to get a new truth value.
can be expressed using just those three connectives. You can build any logical truth function out of just not, and, or.
Wow. So all those 16 binary truth functions we talked about earlier, all those different ways of combining two truth values, they can all be created using just negation, conjunction, and disjunction.
That's right. And that's not all. You can actually be even more minimal. The pair is also truth functionally complete because conjunction can be defined using disjunction and negation.
Using De Morgan's laws.
Exactly. And similarly, neg is also truth functionally complete. So you can build all of classical propositional logic using just or and not, or just and not.
That's amazing. It's like finding out that you can cook any dish in the world using just 3 basic ingredients.
And what's even more remarkable is that historically, Henry Sheffer rediscovered an observation made by Charles Sanders Peirce.
Those are some big names in logic.
They are giants in the field. And they show that even single connectives can be truth functionally complete. Connectives like not both and, often called NAND, and neither nor, often called NOR.
So all of classical propositional logic can be built from just one carefully chosen connective. That's mind-blowing.
It is. It raises profound questions about the simplicity underlying complexity. It suggests that even incredibly rich systems of logic can be built from a very small set of fundamental operations.
It's like finding out that all the complexity of the universe could be derived from just a few fundamental physical laws.
It's a powerful idea. And this concept of truth functional completeness isn't just a theoretical curiosity. It has real-world implications. Our source highlights one particularly impactful application: Claude Shannon's realization of propositional logic in switching circuits.
Ah, yes. This is where the worlds of abstract logic and practical engineering collide.
Precisely. Shannon, a brilliant mathematician and engineer, saw a deep connection between the formal system of propositional logic and the physical behavior of electrical circuits.
And the key insight was the analogy between truth values and the states of a circuit. Right?
Exactly. Shannon showed how you could interpret sentence letters, those atomic propositions, as representing simple electrical circuits.
With each circuit being either open or closed, corresponding to true or false.
Right. And then the logical connectives could be interpreted as different ways of connecting those circuits.
So conjunction and becomes circuits connected in series.
Meaning that the current can only flow if both circuits are closed.
Which, if we associate closed with false, means that the conjunction is only true if both inputs are true.
Exactly. It's a perfect match. And disjunction, or, becomes circuits connected in parallel.
So the current can flow if at least one of the circuits is closed.
Which means that the disjunction is true if at least one of the inputs is true. Again, a perfect match.
And negation not becomes a circuit with an inverter.
So